we have the last about 1 hour left. So I thought I would cover some basic structures of vector spaces, since many of you don't seem to have seen this subject. So is this a good option, or would, so I thought that would sort of unify the other things that we have taught. So what is the reason I stress this notion of vector space a lot is because many of our engineering problems, as you solve more advanced problems, depend heavily on this notion of vector spaces. So the basic idea, we have actually seen these quantities before, but we have not studied it as a formal, under this formal umbrella called vector spaces. So for example, all of us have seen real numbers. We have also seen a string of real numbers. Say there are n numbers. Right? So we call this Rn. All these are vector spaces over what are called real numbers. So the if we forget too much, if we forget a lot of formalism, so if I'll name a vector space V, so the elements of the vector space, so it's a vector space is usually defined over a field. So for the discussion here, let's assume it's just the real field, the real numbers, right? So if you take this Rn that many of you have seen, what are some of the properties it has? So if I'll name this whole vector x, so x means all these things. So if you have your usual addition and add it to another, right? So this gives you another vector in Rn. From now on I'll call them vectors. This gives you another element in Rn. Now x plus y also obeys y plus x. So it has what is called right. Then you also have, if I do x plus y and then add z, that's the same as doing y plus z and adding x, right. So that's called okay. Now there is a special element in this Rn, which if you add to any other element, it would give you the other element. That is, x plus that element will always give you x. So what is that element here? It is the 0, 0, 0, 0, 0 element. So I will call it, okay, I'll call it 0 itself. So x, so there is a unique element 0, such that x plus 0 equals x is the same as 0 plus x, because it's commutative, right. Now for every x there is another element which I will call dash x, such that x plus dash x will give you the 0 element. That is, if you give me any x, I can find you this. You will immediately associate with negative x, right, which will give you the 0 element, right. So that has these properties, but in addition to this, because when I first introduced vector spaces, I said vector spaces are defined over a field of, in this case, real numbers. So where does this field come in? It comes in the following sense. So So, if I call alpha, beta as the elements of the field, so the real numbers, I can associate with alpha from the real numbers and x being any vector in the vector space, I can associate a unique element of the vector space called alpha x. Do not think of it as alpha multiplying x. For the time being, think of it that if I am given a member of the field, an element of the field, which is this, and I am given the vector space element, I can get a new element called alpha x. So, this is called the scalar association, because members of the field are called scalars and members of this are called vectors. Okay. So, I can get an element alpha x. Now, these members of the field, they have properties by themselves. So, I have properties such as this: alpha plus beta x equals alpha x plus beta x, then alpha x plus y is alpha x plus beta y. In these arguments, please remember the following thing: this alpha plus beta is giving you a member of the field, because the field themselves, they have two operations, binary operations, which I will denote as plus and cross for the multiplication type. So, this is giving me a member of the field, and this is giving me the association of that member and x. That this expression is saying is the same as association of alpha with x. Now, this becomes a vector, and this is the, okay, I probably did not mention this right at the beginning. The first thing is the binary operation between vectors, this plus sign here, right. So, this is a vector, this is a vector, I can add it. Here there is a scalar, but this is a vector. This association is the same as this and this association plus this one. So, you have rules such as these. So, let me make sure I have not missed out anything. Alpha x plus y and yeah, I think I have most of them here. Yeah, and in this set which is called the field, there is an identity element as well as there is a 0 element, which I will call as this 0, not to be confused with this. So, for every alpha which is not this 0, I can find an alpha inverse, so that this with the binary operation, with one of the binary operations in the field, will give you this. And there is also a distributive law, I should try to remember what that is. Well, anyway, we have the main properties here. Oh yes, so this element has the property that 1 associated with any vector x will give you the same vector for all vectors. So, now look at, so let us consider So, we are saying we will consider the field to be real numbers and the vectors to be just Rn. So, notice you will have all these properties satisfied 1, 2, 3, 4, this one, this one, this one, all of them. Now, let us take another example which is different. So, let us consider example 2. Consider the set of continuous real valued functions over the interval zero, 1. Nothing special about this interval, it is just that I have chosen. So, consider the set of all real valued functions. So, let me say if I take a function f, it basically means that this f, if I plot it this 0, 1. So, this is the x argument. So, this is f of x. So, maybe it has that could be f of x. Now, take the set of all such functions. Do you think they form a vector space over the real numbers? And if yes, what would this operation be? What would that binary operation be? Suppose I gave you two functions f1, f2, both of which are continuous over 0, 1. How would you define that function? f1 plus f2. Simple, right? You can define f1, f2 as pointwise, right? You can say this is nothing but because both these are defined over 0, 1. So, the new function f1 plus f2 is that. Now, with that operation, is this true, the first property? Yes, indeed, commutativity is true. Associativity? Yes, indeed. What is the equivalent of 0? What is the equivalent of that 0 element? It is just a function which is 0 everywhere from 0 to 1. So, it is a function like this. Zero everywhere. So, it is the function. So, let us call it f0, x equals 0 for every x in this interval, correct? Now, what about these? Suppose I take an alpha and I have a function. How would I define a new function? Remember, that is what you need to do, associating a scalar with a function. How would I define that new function? Simple, right? Alpha f x is alpha in my usual multiplication to f x. That is my new function alpha f, right? And you will see all the other properties are satisfied as well. So, now here is a non-conventional or what you have not seen before as a set of objects which forms a vector space, right. So, similarly I will give you another example. Is that clear? The second one, is that clear? Okay. So let us take another example. So consider polynomials in the indeterminate t. So polynomials expressed in t of order less than equal to 3. So how do they look like? How does a polynomial, let us call it x in, yeah, so it will less than equal to 3 means a 3 look like this, right. Now could I make the set of all polynomials of degree less than equal to 3 a vector space? If yes, you will have to give me first the binary operation between two polynomials and the scalar association, and also whether all those rules are satisfied. Could you tell me what would the binary operation be between polynomials? Suppose I gave you this polynomial x and I gave you another polynomial y. How would you define a binary operation? Yeah, can you tell me exactly how addition?
Coefficients of each of the.
Yeah, perfect. So you will sum up the coefficients of similar indices, right, similar exponents. So that is fine. So this will become x plus y becomes similarly, right. So that comes that. Now what is the 0 element yourself? What is the 0 element in this set of polynomials? You are not sure? Can you take a guess what it could be? Yourself. What is the 0 element in this set of polynomials? One second, let me just give some. It's just the 0 polynomial, right? Take a polynomial with all this coefficient 0, right? You'll agree with me that x plus 0 will give me x, correct? Do you see that? 0, I mean a polynomial, please remember, is not that you are substituting values of t here. This is just an object. You are not substituting some t and finding a number. No, you are not doing that. Please do not confuse it for a function. It is just an object like this, and as you said, when you are talking of addition between two objects, you are adding coefficients of similar degrees, right? That is all. That is a 0 polynomial. So what about scalar association yourself? How would you associate some scalar alpha with some polynomial x which looks like this? Yourself? Yes. A? E0. Okay, A0 and no, I mean it's simple, right? Alpha x will just be alpha A3 Clear? Okay. Can you give me an example now of a vector space yourself? Some other example. I have given you 3. What you had seen before, Rn, then I gave you continuous functions, then I gave you polynomials. Can you give me some other example? Yourself. Set of all matrices. So, once you say that, you will also have to give me the binary operation. Yes, set of all matrices means dimension you will have to give me first. N by N? Okay. 2 cross 2, okay. Set of all matrices, call it A. So, okay, let us call it R 2 by 2, okay. What is the binary operation? Yeah. So, A plus B, component wise you will add, okay. Component wise he says you add up. What is the 0 element? All entries are 0, perfect. So, for every A will you have a negative A, so that A plus the negative A will give you 0? Yes, you will, because you take the negative real number, that is fine. So, that should be okay, right? That all right? Okay. Any other example? Okay. So, now so in addition, so this is the basic definition of a vector space. There are some properties of a vector space which sort of are used very often. You might have heard in our lectures before the word subspace. So, what is a subspace? So, if you have a, let us consider the vector space R3, right. Now, let me consider the following set. That is all possible combinations of these vectors, right. All possible combinations of these vectors, since alpha beta are real. This is like saying, consider this room. Let me take this as the origin. I will take this as the x axis, y axis, z axis. This is like a unit vector in the x axis, unit vector in the y axis. Alpha plus beta of this for all possible alpha beta is the entire floor, leaving out the z, right. Now, this set is called a subspace. Why is it called a subspace? Because if I take any 2 elements in this set, the sum of those elements will also be in that set. If I take any 2 elements, even the linear combination of those elements will be in this set. So, formally the definition of a subspace goes like this. A subset S of V, a subset F of V is called a subspace is called a subspace of V, V being a vector space, if for every x and y belonging to S, for every x and y in S, alpha x plus beta y, the linear combination, belongs to S for every alpha beta belonging to the real numbers. That is a definition of a subspace. So, in the set of polynomials of degree less than equal to 3, can you give me an example of a subspace there? Circle polynomials. Polynomials of degree, remember I have erased it, it was like this. Subspace. Anybody else? Yourself? Yeah, perfect. So, he says consider S as all pollen. So, degree less than equal to 2 means I will say A2t squared for A2, A1, A0 being real numbers. Perfect. This is a subspace in the subspace of polynomials. Do you see that? No? Okay. Can you give another example now? What about yourself? Yeah, that's, you'll have first, second, that's true. Anything else? So, you could give it in a different way. You can, let's, okay, maybe we will move on to considering something else. So, let's, so this is the notion of a subspace. Now, another very important notion in vector spaces is the notion of a basis or a set of coordinates. Just like when you take R3, the natural basis that you refer to is 1 0 0 0 1 0 0 0 1. So, in the same way, the notion, so the basic properties of a basis of a vector space are the following. So, a set S as, okay, a set B, let us say, a set B of a vector space V is called a basis if it has the following properties. One, every vector in V can be expressed every vector in V can be expressed as a linear combination of the elements in V. Two, B is a linearly independent set. I have not explained this to you, but I am assuming that most of you know this meaning. B is a linearly independent set. How many of you can give me a basis for R3? Give me a basis for R3. Remember this set B, which is a basis. So let me give you so let me start with R3. So one basis is this. Give me another basis. Give me some other basis. Yes. Okay, any multiple of this. So another basis would be, so if I call this first, this is also a basis, right? Perfect. Suppose I had removed this element here, would that still be a basis? Which of these rules would it violate? First one, it would violate the first one. Now suppose in addition to this I had another vector, would that still be a basis? No. Which of these rules would it violate? The second one, right? It would not be linearly independent. So now in the set of the vector space of polynomials of degree 3 or less, can you give me a basis yourself? Can you give me a basis in the vector space of polynomials of degree 3 or less? No, not sure. Okay, anybody? Anybody? Yes. You have to be specific. You have to be specific. Can you please specifically tell me what it is?
We take only one degree polynomial coefficient and the other are 0.
Okay, tell me. B.
Highest degree polynomial we take one and every other 0.
Okay, that's perfect. So you are saying take it as t cubed, t squared, t 1. Is this a basis? Is it linearly independent? Yes, it is. Can every polynomial of degree 3 or less be expressed as a combination of these? Yes, you can. Is that understood? So that's a basis. I gave you the example of a vector space of continuous functions. Can you give me a basis for that? Continuous functions on the interval 0, 1. Yourself? Not sure. Okay. Yeah, there seems to be some problem now with continuous functions. Why? Because all the examples I gave you earlier are what are called finite dimensional vector spaces. Finite dimensional vector spaces means the basis will have a finite number of elements. But now when I give you continuous functions on the interval 0, 1, there is no finite basis. I can give x, x squared, x cubed, I have to go on. There is no finite, so it's called an infinite dimensional vector space. Like continuous functions over some interval, differentiable functions over intervals, they are all infinite dimensional vector spaces. So if you start writing a basis, there's no, you keep on writing it. I mean this. Do you see the difference? Okay. All right.
Then we can write x to the power n values from.
But n would go on, yeah. and even there you would not include some types of continuous functions which may not be expressed as sums of such x, x squared, x cubed and so on. Okay. So, the dimension of a vector space, now it is another term, the dimension of a vector space is the number of elements in a basis. So, it follows that the number of elements in any basis for a given vector space will always be the same. For instance, when we took different bases here, forget this, so all 3 elements were there, right. The number of elements in any basis, a basis for a vector space is not unique. The number of elements in any basis of a vector space is, the number is unique and is called the dimension of the vector space, right. Therefore, the vector space of continuous functions over the interval 0, 1 was an infinite dimensional vector space. The other quantity you have been seeing in these courses is a notion of a norm. Now, why do we need norms? Because we want to associate a notion of size with a vector. Suppose I gave you a function. Immediately it is not clear to you what is the size of a function, right. So, you associate something called a norm. So, a norm is denoted like this, assigns to a vector a non-negative, it cannot be negative, greater than equal to 0 real number with the following properties, that x plus y right and x equals 0 if and only if x is the 0 vector and alpha x, where alpha is a scalar, for x. So, on R3, give me a norm. All of you have seen something called the Euclidean norm. So, if I give x, so if x was like this, does it satisfy all these 3 properties? This does not seem to be very obvious, but you will have to check. This is obvious, this is obvious. Give me some other norm on, so this is called the Euclidean norm, so it is usually put as 2, the 2 norm. Give me some other norm on R3 yourself. Huh? Any even number of what? Suppose I gave you x, what is the norm? 4th power of what? No, that is not correct. Well, you have something called a p norm, but I am not getting into that. I will give you a simpler quantity, x1. What is that? Does it satisfy all these properties? The first one. Can you check, does it satisfy the first one? If you take x plus y, what is it? So, you will have a vector like this. Right? Norm of this according to this will be right. Now, each of these will always be less than equal to the individual sums, right, of absolute values, right. And now bring this together, this together, and did I make some mistake? Sorry, bring this and this together, this and this together, and you will have the answer, right? Should be true. So, that is the notion of size. Now, in all this discussion so far, we have never considered a notion like an angle between vectors, and that is given, or the notion of two vectors being orthogonal, and that concept, which is an extension of your what you studied as an inner product in physics between two vectors in R3, is extended to vector spaces to define what is called an inner product. Okay. Now, an inner product in a vector space, I will represent it by this angle, takes two vectors, right, it takes two vectors and gives you a real number. In this case, we are on real vector spaces with the following properties. It has to satisfy Z. So, this actually, when it is a complex vector space, it is complex conjugate of this, and 3 is yes. So, can you give me an inner product on? So, here it is the way. So, there are a basic few properties of vector spaces. So, that gives them a lot of structure, but then you introduce a norm, you give additional structure to the vector space. You introduce an inner product, you give additional structure. So, with the in R3, let us say, what is the inner product that you have seen? The scalar, it is the scalar product, right, you multiply the element. So, if the inner product of two elements in R3 becomes 0, it means what? They are orthogonal to each other, they are perpendicular. So, therefore, This generalization of the inner product brings in notion of orthogonality to other vector spaces. For example, if you have function spaces, so you can set up an inner product. This is the origin of Fourier series and Fourier expansions, etc. If you set up an inner product, you can make two functions orthogonal to each other, right? So that's the notion of things here. So I think I've tried to cover the essence of what is vector spaces. If you wish to look up more issues or more topics in this, please refer to some of these books. And this has a more formal treatment, finite dimensional vector spaces. Then this is second one is also a very good book with plenty of problems, a lot of problems. So if you wish to give it, some of you who are college teachers wish to give it to your students, I mean, it's a very good book. The linear algebra that every graduate student should know is the title of the book. I used it last semester for my course, so it was quite nice. Should know or ought to know, I am not sure. It's by Jonathan Golan. At the end of each chapter, he has a minimum of 50 problems. So there are about, I think, over the entire text, I don't know how many he has. So he gives you everything that's required. If you do the problems in this, nobody can shake you in vector spaces. Every aspect of vector spaces. But to understand from a formal point of view and very rigorous theory, this is a nice book. This is a classic. This was written maybe 30 years ago. This is a recent book, so this is just about maybe 3-4 years ago. So with that, I think I will call it a halt.